Welcome to our deep dive, into this fascinating world of determinants. They may sound a little intimidating at first glance, but trust me, once you kind of grasp their power, you realize they're a real game changer in math. Like they
Right.
simplify complex problems,
Yeah.
which is always a good thing, right?
Yeah, absolutely. And what's really cool about determinants is they're not just, some theoretical concepts stuck in a textbook. They have real world applications and, these surprising connections to all sorts of fields. It's like this hidden language for understanding the world around us.
Okay, so before we go too deep down the rabbit hole, can we start with the basics?
Right.
What exactly are E-determinants? I keep picturing like some big scary equation with a ton of Greek symbols. Am I on the right track?
Not exactly. Imagine you're at a party, it's super crowded, everyone's talking at once. A determinant is like a tool that lets you focus on one conversation. You can isolate and analyze it even with all that noise around you.
I like that. So instead of a room full of people, we've got a set of equations. And the determinant helps us find the solution that works for all of them, right? Like cuts through the clutter.
Exactly. Visually, you can think of determinants as these arrays of numbers. They're arranged in rows and columns like a spreadsheet almost. And using a specific formula based on these numbers, we can calculate the determinant's value.
So the determinant itself has a value. It's not just about finding any solution. It's like this special number that tells us something important about the equations.
You got it. The value acts like a signal or a flag. It tells us whether the equations have a unique solution or multiple solutions or maybe even no solution at all.
Okay, that's starting to make sense. So far, determinants sound pretty useful. I'm guessing there's more to it than just the value, though. What about this structure with the rows and columns? How does all that fit in?
Yeah, so the arrangement of those numbers is really key. And just like conversations at a party can have different numbers of people, determinants come in different sizes depending on how many equations and variables are involved. We call these sizes orders. So you might have a second order determinant for two equations and two variables, a third order for three of each, and so on.
So the complexity of the problem basically determines the size of the determinant we need. It's like picking the right size wrench for a bolt.
That's a great analogy. You wouldn't use a giant wrench on a tiny screw, right? Same with determinants. You wouldn't use a huge one for a simple problem.
Makes sense. So we've got these arrays, different sizes, all that. But how do we actually calculate the determinant's value? Is there some giant messy formula?
Well, the formula can look a bit intimidating at first, but there are ways to make it manageable. Like for third-order determinants, there's something called the Saris diagram. It's a visual tool that makes the whole process more intuitive.
Visual aids in math. I'm intrigued. Okay, so we've got the arrays, the sizes, the visual tools. What else is there to this determinant adventure?
Next, we delve into a couple of key concepts. Minors and cofactors. They might sound a bit mysterious, but they're essential for understanding how determinants really work.
Minors and cofactors. Those sound interesting. Are they like hidden clues within the determinant itself?
You could say that.
Hmm.
Imagine a Sudoku puzzle. Each number in the Sudoku is linked to a smaller puzzle, right? Minors and cofactors are kind of like those smaller puzzles within the bigger picture of the determinant.
I'm with you. So we're breaking down a big problem into smaller, manageable chunks.
You got it. A minor is basically a smaller determinant. You get it by removing a specific row and column from the original one. And then a cofactor, it adds a plus or minus sign depending on its position. There's a formula for calculating it, but the main idea is each element in the determinant has its own cofactor.
So each number in the array gets a plus or minus sign. That's pretty cool. I see how these smaller pieces are fitting into the whole puzzle.
Exactly. And once you get minors and cofactors, you unlock all these incredible properties of determinants. You can use them to simplify all sorts of calculations.
Okay, now you've got me really curious. Let's talk about those properties next. I'm ready to see what these determinants can really do.
So, one of the really powerful things about determinants is that they help us simplify complex calculations. It's like having a set of master keys, to unlock these shortcuts in math.
I like the sound of that. Math shortcuts are always welcome. Can you give me some specific examples? How do these master keys actually work in practice?
Okay, so remember how we talked about determinants being able to tell us if a system of equations has a unique solution? Well, if two rows or columns are identical or proportional, that determinant's going to be zero. And that's a sign there might not be a single solution.
Right. It was like a red flag telling us to be careful.
Exactly. Now, let's say you're working with a system where the determinant isn't T0. That means there's probably a unique solution. And you can actually use determinants to find that solution directly without a ton of algebra. It's called Cramer's rule.
Kramer's rule. Okay. Sounds important. A rule named after a mathematician. Can you walk me through how it works?
Sure. Think of it like a recipe with specific steps. First, you calculate the determinant of the main system of equations. We'll call that D.
Okay, so that's our starting point, the determinant of the original problem. Got it. Then what?
Then you create new determinants, one for each variable you're trying to solve. Let's say we're solving for x, y, and z. You'd create D1, D2, and D3.
3 new determinants, one for each unknown. How are these new ones different from the original D?
Good question. You form them by replacing the coefficients of the variable you're solving for with the constant terms from the equation. So for D1, you'd replace the coefficients of x with those constant terms.
Ah, I see. So we're basically swapping out parts of the original determinant depending on which variable we're focused on. Kind of like rearranging a puzzle to find a specific answer. What happens once we have these new determinants?
Now here's the cool part. To find the value of x, you just divide D1 by D. For y, it's D2 divided by D, and for z, D3 divided by D. Super straightforward.
Wait, that's it? Just a few divisions and we have the solutions. Determinants really are like magic.
That's the beauty of Cramer's rule. It cuts through all that tedious algebra and gives you a direct path to the solution, as long as the determinant D isn't 0, of course.
Right, so that 0 determinant, which was a warning sign before, is actually crucial information for using Cramer's rule. It tells us if this shortcut even works.
Exactly. And there's another situation where determinants are super helpful: homogeneous systems of equations.
Homogeneous, I remember that term. It's where all the constant terms are 0, right?
You got it. So in a homogeneous system, all the equations equal 0. And these systems always have a solution where all the variables are 0. Kind of like saying, if everyone's quiet, there's no conversation happening.
Yeah, that makes sense. But I imagine sometimes we want more than just silence. How do we know if there are other solutions where at least one variable isn't 0?
That's where determinants come in again. For a homogeneous system to have those other solutions, its determinant has to be 0. So that 0 determinant, which was a warning before, is now actually a requirement for these special solutions.
So the determinant's role changes depending on the problem. It's like a chameleon adapting to the situation. This is making me realize that determinants aren't just a tool. They're like a language for understanding equations and solutions at a deeper level.
I love that way of thinking about it. They help us see those relationships between variables and constants and solutions in a way that regular algebra sometimes misses. And speaking of relationships, earlier you mentioned determinants having these surprising connections to geometry. I'm really excited to dive into that.
Yes, let's explore that. You mentioned using determinants to calculate the area of a triangle, which blew my mind. I still can't quite picture how an array of numbers can describe a shape.
It is pretty cool. It all comes down to how we represent points in space using coordinates, like on a map, with grid lines.
Right, so each point has an x-coordinate and a y-coordinate.
Exactly. Now imagine you've got 3 points that form a triangle. You can create a determinant using those coordinates, and the value of that determinant will be directly proportional to the area of the triangle.
So the determinant's capturing something about the arrangement of the points, not just their individual values. That's incredible.
It is, and it gets even cooler. If the determinant of this triangle is 0, it means the 3 points are actually on a straight line. We call that collinear.
So it's like a collinearity detector. That could be so useful in geometry.
Absolutely, and there's more. Determinants can also tell us if 3 lines are concurrent, meaning they all intersect at the same point. So we're not just talking about points and triangles, we're looking at whole lines in space.
Wow, determinants are like a Swiss Army knife for geometry. Points, lines, triangles, what else can they do?
Well, there's a whole world of special types of determinants out there, each one with its own unique properties and applications, like cyclic determinants, where the elements have this repeating pattern. Those are really useful in fields like physics and engineering, where you often see things that cycle or repeat.
Cyclic determinants, I'm intrigued. What kind of real-world problems do they help us solve?
They pop up all over the place. From analyzing oscillations and waves in physics to studying systems with feedback loops in engineering, they're great for understanding complex systems that have these repeating patterns.
It seems like the more we learn about determinants, the more versatile they become. It's like there's this hidden language connecting all these different areas of math and science. And it's amazing to think something as simple as like an array of numbers can have so much power and so many applications. Determinants are the secret code to unlock the universe or something.
I love that. And, the more you dig into determinants, the more you realize it's not just about the calculations or finding the right answer. It's a whole way of thinking, a framework for understanding how complex systems work.
That's what's been so cool about this deep dive.
Right.
We're not just memorizing formulas, we're seeing things from a whole new perspective. It's like we're learning to see the world through a different lens.
Exactly. And that shift in perspective can be so powerful, not just in math, but in any field. Analyzing, data designing experiments, even just making sense of the world around us.
Absolutely. So as we wrap up our determinant adventure, what are some key things you hope listeners will take away? What makes these arrays of numbers so special?
Well, first, I hope people will appreciate how elegant and simple determinants really are. They give us this concise way to represent even really complicated systems of equations, like compressing a whole paragraph into a single symbol.
It's like a shortcut for expressing big ideas
Yeah,
then.
exactly. And second, I hope people remember how versatile determinants are. We've seen how they can solve equations, uncover geometric relationships, and even analyze those complex systems in physics and engineering. They're like a multi-tool for math.
They really are. We started with this abstract concept, and now we see determinants popping up everywhere. It's like realizing a simple tool can solve all sorts of problems.
And finally, and maybe most importantly, I want people to remember that determinants aren't just a tool for calculation. They offer a way of thinking, a framework for understanding relationships, and finding patterns we might otherwise miss. Like learning a new language that lets you see the world differently.
That's a perfect way to put it. It's not just about the math, it's about the insights those calculations give us, understanding the deeper structure behind it all.
Exactly. So to everyone listening, I encourage you to keep exploring determinants. There's so much more to discover, and who knows what other amazing connections and applications are out there.
This has been an incredible journey. I'll admit I was a little intimidated by determinants at first, but now I'm truly amazed by them. Thanks for being such a great guide.
It's been my pleasure. And remember, the world of math is full of these fascinating ideas just waiting to be explored. Keep that curiosity alive, and you never know what you might find.
That's a great thought to end on. Thanks for joining us on this deep dive into the world of determinants. Until next time, keep exploring and keep learning.